The purpose of this video is to introduce you to best practices for how you will be expected to make graphs in physics. Key points at the beginning. When making a graph, you should work with grid paper. You should be using grid paper at all times when making graphs. In fact, this is why we have requested that you use a Quadrile notebook for your lab book and for your notes. Second thing, your graph should be full page, using as much of the space as possible. I understand that it seems like a tremendous waste of paper to you now, but you should make your graphs as large as possible. You will be much happier with the results in the end. So I have set up here an entire page where I'm going to make this graph. Your graphs will actually be bigger than this because your aspect ratio is opposite. So you will have your longer axis up potentially, and your horizontal axis will be bigger. As a rule, which I have not followed here, but as a general rule, you should choose the orientation of your paper according to the size of your scale. Here, my x-axis goes from 0 to 1, where my y-axis goes from 0 to 5. Because my y-axis is longer, I would generally like my y scale to be longer than my x scale. So if I were making this graph on paper and pencil, I would have my paper oriented in the portrait position so that my longer axis would accommodate my position information because it is the larger number. So those are key points. We should use grid paper. We should make it full size. Another thing you should keep in mind is that the graph is not the purpose. We do not make a graph as an end unto itself. The graph is a tool that we use along the way. The goal is to find the relationship between these two variables. And by relationship, I mean equation. So we create a graph so that we can go and find the equation that relates one variable to another. So when making a graph, don't think, oh, I made my graph, I'm done. Make it as well as you can because it is a tool we use to go on to get the actual answer we are looking for. So when making a graph, this is the data we're going to work with, but this is simply an example. I'm going to try to be general enough that this will work for any graph you would like to make. The key here is setting up a scale, a good scale that will fill as much space as possible without being too obnoxious. So, setting up our X scale, we need to run from 0 to 1. The first thing I'm going to do is count how much space I have available. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29 boxes. Gonna be honest, 29 is a bit of an obnoxious number, especially when we're dealing with 1. 1 and 29 do not communicate well with each other. However, this is sort of the trick of this, is you need to say, well, what is close to 29? I can't go to 30. 30 would be okay, but 30 doesn't exist. It's out here somewhere. It doesn't exist. So what is smaller than 29 that communicates well with 1 or some multiple of 10 of 1? Well, 25 comes to my mind immediately. 25 and 1 communicate quite well together. So here's 29, 28, 27, 26, 25. So if I take at my 25th box and say, look, there's 1.0 right there. This is going to set up a nice scale for me. From 0 to 1, it's going to take up almost the entire axis. And when I look at, well, what are my individual divisions worth, I see that I take 1 second, divide it up amongst 25 boxes, which gets me quite a nice arrangement. It's not perfect, it's in no way ideal, but we're talking about a 4 here, right? This should get us 0.04 as a value for each box. Let me make sure that is correct. Picking up my calculator. Yes, so this tells me that each individual box, 0.04 seconds per box. So going back to my graph, this is my scale. This is the constant ratio that represents my scale. Each one box on my scale represents 0.04 seconds. So here, and this is temporary, you should make graphs in pencil so that you can make adjustments when necessary. There's 0.04 seconds. Well, this is a little bit of an obnoxious number. We would like a nice round number that's easy to work with. Well, I have 4. I would like to multiply 4. Pick some number of boxes that when I multiply by 0.04, I get a nice neat number. How about 5? 0.04 times 5. What do you get when you do that? So again, I don't want to label every single box. There's not enough space. So I want to choose a number of boxes to label that gives me a nice, neat number. Times, if I multiply this by 5 boxes, I get a nice, neat number, 0.4 seconds, or 0.2 seconds. 4 times 5 is 20. You have your decimal places, and there it is. So every 5th box, 1, 2, 3, 4, 5, every 5th box is worth 0.2 seconds on my scale. 5, so there's 0.04, 1, 2, 3, 4, 5. There's 0.06, 1, 2, 3, 4, 5. There's 0.08. And we see that this works out very neatly. 1, 2, 3, 4, 5. There's 1. Your scale should work. Now I'm going to erase this. We don't need that anymore. That was sort of scratch work. This is why we work in pencil. You can make scratch work and say, okay, how's this going to work out? Maybe it doesn't work, make adjustments, and fix it. So here we have a nice scale that spans basically the entire available space. It's even. An even scale is absolutely essential. One box is equal to however much it is, no matter if it's this box here at the beginning or this box at the end. Every box must have the same value or you don't have a real scale. I don't have a great way of explaining why that's important. It is. It's essential to a graph. Okay, so our x-axis works out quite neatly. And as we look at our x values in this particular example, they're very neat and tidy. If I want to graph 0.1 seconds, it's right here, halfway through. There's 0.1, 0.2, 0.3 is exactly halfway in between, 0.4, 0.5, 0.6, 0.7 is here, 0.8, 0.9, and 1. So these points are there. I've indicated with a small mark where those points are so that when I go to plot my y value, I know where they are. In this particular example, these work out very neatly, so we don't have as much work to do. Now we have to set our y scale. We run from 0 to 4.85. I'm going to round these all off to the hundredths place for the purposes of this exercise. This is, again, a bit of an obnoxious number. We don't need to fill the entire space. We want to fill most of the space. So what I'm going to do is I'm going to round a little bit. Instead of 4.85, I'm going to say, look, we need to go to 5. If we go to 5, that'll be close enough. We're going to use most of the space. It'll be fine. So I need to say, well, I'm going to put 5 out at the end, and then we'll figure out where all of these go. So just like on the x-axis, we need to count how much space do we have available. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Well, doesn't that work out just perfectly? 5 and 20 go together exceedingly well. Times 4, right? Every 4 boxes will be 1. So let's look at that. We're going to take 5.0 meters and we're going to divide it up into 20 boxes. 5 divided by 20 tells us that each individual box is 0.25 meters. 0.25 meters per box. If I take 4 of those, 4 boxes times 0.25 meters per box is 1 meter. 4 boxes on our scale is 1 meter. That's quite a nice scale. So let's go back and look at it. 1, 2, 3, 4. There's 1 meter. 1, 2, 3, 4. 2 meters. 1, 2, 3, 4. 3 meters. 1, 2, 3, 4. 4 meters. 1, 2, 3, 4, and there's our 5 meters. There's a little bit of rounding. This is a bit of an art form. You have to practice and learn how do I make a reasonable scale that's easy to read and easy to work with without shrinking it up so small that the graph is going to be completely useless. So now we have our scale set. Okay, so I'm going to highlight this so that we can see. On the x-axis, 1 box is 0.04 seconds. This is on our x-axis. This is the scale for our x-axis. On the y-axis, we have this. This is the constant ratio. It is the relationship between the number of meters and the number of boxes. The number of meters in reality, the number of boxes or tick of grid lines on our graph. These are the scales we have to work with when we go to plot our points. Now that we have our scale set up, we are ready to actually plot these points. We're going to start with our first one, which is fairly self-explanatory, 0, 0. There's 0, 0. We place our point, and then we add a point protector. The purpose of this point protector is that we're not going to draw or do anything inside of this area. I've made it a little larger than I would if I were actually doing this with paper and pencil. I would make a fine point that's visible, but a fine point exactly where it's supposed to be. And then I would make a small circle around it to protect that point from anything else. The idea is that we want to be able to clearly see where the point has been placed with no lines or anything else getting in the way of that. So that's the purpose of a point protector. So there's our first point. For our other points, this is a little more complicated. Well, where does this point go? Point 1, okay, well there's point 1, great. But where in the world is 0.05? I'm going to round off to the hundredths place, as I've said before. How do we know where to put this point? Well, we could guess, but we're going to avoid guessing, and we're going to instead calculate. We're going to calculate and approximate. We're not going to guess. We're not going to be like, oh, well, that's close enough. There's no close enough. Calculate and approximate. So we're going to use our scale. The point we're looking for on our y-axis is 0.05. So I'm going to go forward to where I'm doing my work. Here's our relationship. We can use this one or this one. It's the same ratio. I know that 0.25 meters is 1 box. What I'm interested in is, well, where is 0.05 meters? Make sure that is correct before going forward. Yes, that is correct. If 1 box is 0.25 meters, how much is 0.05 meters? Well, this is a ratio that we can solve by cross multiplication. 1 box times 0.05 meters divided by our third one. There's actually a video that will be posted on how to solve these. If you are unfamiliar with solving ratios, you can check out my channel. There is a video on how to solve ratios, specifically using cross multiplications. Please go check that out. But 1 box times 0.05 meters divided by our remaining number, 0.25 meters, tells us that we want to place this point at 0.2 boxes. 0.05 meters is 0.2 boxes. So when I go back to my graph, I don't have to guess where to place this point. There's 0.1, and I want to be just short of 1/4 of a box. Place my point. Add a point protector. Moving forward, 0.2. I don't have to worry about the x-axis on this particular data set because they're so evenly divided and they're well defined, which is nice because then we only have to worry about the x-axis. So let's look here, 0.194. So we're going to round that off to 0.19 using the same ratio. Well, if 0.25 meters is 1 box, where is how many boxes is 0.19 meters. How many boxes is that? Don't know. Well, we can again solve this by cross multiplication. 1 box times 0.19 meters divided by 0.25. And we find that that is 0.76 boxes. So we're talking about approximately 3/4 of a box. So we got to 0.2, and we go up 3/4 of a box. This may seem a little bit obnoxious to you. I understand that. When I first learned this, this was obnoxious as well. But we're solving a ratio and approximating. We want this graph to be as high quality as possible because it is a tool to get us to the result we want. We are looking for the equation that relates these two variables to each other. We're not just trying to make a pretty picture. If we make a pretty picture, but the picture does not actually relate back to the relationship we're looking for, we've accomplished nothing. We have to make a very high quality graph. Moving on. 0.3, 0.42. We're again looking at the y-axis. The same ratio holds for every single point. 0.042 or 0.42. 0.42 meters is how many boxes? It's the same ratio all the way across. 1 box is 0.25, so we solve this by cross multiplication. 1 box times 0.42 meters divided by 0.25. We find that that is 1.68 boxes. So that is just shy of 1 3/4 boxes. We come out to 0.3, 1, and short of 3/4, about 2/3 boxes. We make our point protector and we can start to see the shape of this graph. 0.4. So I'm going to do my work here and then erase it. This is why we work in pencil. We know that 0.0. We know that on our y-axis, 0.25 meters is 1 box. So for 0.4, where is 0.79 meters? Solving by cross multiplication, 0.79 divided by 0.25. And you should start to feel like, wait a minute, this is really redundant. We keep doing the same exact calculation over and over and over and over again. That's why this isn't really that big of a burden. You're simply doing the same calculation over and over. There's 1, 2, 3, and that's about a 1/6, but in the first quadrant, we want to get this close. You got to be within a quarter of where you should be. So there's that one. Scratching the work. Going on to 0.5. If this is 1 box, where is 1.18? Add an extra decimal point in there. That's, decimal points are on sale this week. It's Labor Day. Same ratio, same way to solve it. 1.18 divided by 0.25. We find that that is 4.72, about 4 3/4. 1, 2, 3, 4. And just more than 2/3, about 3/4. There's our point. 0.6, 1.68. 1.68 meters is how many boxes? 1.68 divided by 0.25. The ratio is going to be different for every graph. However, there will be a ratio for each axis on each graph, and once you have it, you simply use it to plot all of your points. 1, 2, 3, 4, 5, 6, and just short of 3/4. The next one, 0.7, 2.38. 2.38 meters is how many boxes? 2.38 times 1 box divided by 0.25. Same ratio, same way to solve it. That's 9.52. 1, 2, 3, 4, 5, 6, 7, 8, 9, and basically a half. erasing my work, or where if I were doing this on paper, I would be using a piece of scratch paper, but I'm doing it here so that you can see it on the video. 0.8, 3.04 meters is how many boxes? One box times 3.04 divided by 0.25. That is 12.16 boxes, so basically 12 and a sixth. 4, 5, 6, 7, 8, 9, 10, 11, 12, and just a skosh. There we go. Next one, 0.9, almost done. 4.05. 4.05 meters is how many boxes? 4.05 divided by 0.25, and we find that is 16.2, so basically 16 and a quarter. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and right in there. Again, we're not perfect, but we're getting it. Each dot is within the right quadrant of our graph paper. Erasing that work, and on to our last point, 1 and 4.85 is how many boxes? 4.85 divided by 0.25, find that is 19.4. We know that's 20, so just shy of half. All right, so now we have our points plotted. Many of you will at this point be tempted to connect the dots. This is not second grade. This is not a connect the dot exercise. Never in your life again connect the dots on a graph. We are looking for a single equation, not a piecewise function, a single function which represents this curve. It represents the relationship between this data set and this data set. As I look at this, there's one word screaming into my mind, and the word is parabola. This is half of a parabola. This is a quadratic relationship. 90% of the time, if I see this shape, it is going to be a quadratic. It might not be. That might be wrong, but what I'm looking at here, there's no reason to believe it isn't a quadratic. We will deal with in another video how you actually sort that out. Right now, we just are interested in how do you make these graphs. Key point, do not connect the dots. You want to take your pencil and make one smooth, continuous line through the points. But here's the trick. Don't write inside of the point protectors. So we want one curve, but it's like we want to stop at the beginning of the point protector and then pick up again on the other side, and do this without connecting the dots. I'm going to try this. This is very difficult on the computer. It is much easier with paper and pencil. So I expect that your efforts with paper and pencil will be better than my effort on my computer here, because this is not an easy thing to do. Remember, you are not connecting the dots. You are attempting to draw one parabola which is interrupted by the point protectors so that we can see where the point is supposed to be. So here is the curve that represents this relationship. We would then go on to find this relationship, and that will be the topic of another video. For now, our goal is, can you make this graph? If this were a linear relationship, you would go ahead and search your line, pick 2 points, and actually find the equation of this graph. And that will, again, that will be the topic of another video, not this one in particular. So, key points before we end. Use grid paper, first point. Second point, your graph needs to be full page. Take up all of the available space. Third point, your scale must be even. No matter where you are on your scale, each box must have the same value. You can have different scales for your X and Y axes, as we have here. On this scale, 5 boxes is 0.2 seconds. On the Y scale, 4 boxes is 1 meter. But the key is that these 4 boxes and these 4 boxes have the exact same value. These 4 are worth 1, these 4 are worth 1, these 4 are worth 1, these 4 are worth 1. These 5 are 0.2, these 5 are 0.2, these 5 out here are 0.2. Scales must be even. The shape of your graph will be wrong unless your scales are even. When you plot your points, use your scales, solve ratios, and then approximate the position of the dot. Don't guess. No guessing. Work a ratio, plot the point according to the ratio. Do not connect the dots. Draw one smooth curve of best fit. If it's a line, use a ruler. Place the ruler, draw the line. Do not go inside of your point protectors. When you get to the edge of a point protector, pick up your pencil, move to the other side, put it down, keep drawing. But again, we're trying to have one smooth curve, not a bunch of piecewise functions. And that is how you make a graph. Finishing up here, getting in all of our other important features. What have I graphed here? I don't know. We'd better give it a title. This graph is position versus time. There's a general rule here. Y variable versus X variable. Dependent variable versus independent variable. A variable that is affected versus the variable that is doing the affecting. This is a good, clear title that shows us what we are looking at. We also need axis labels. What's down here? These are just numbers at this point. Pure numbers, they have no meaning. The graph should have meaning. This data comes from an experiment. I didn't pluck it out of the sky. This is experimental data. We did something in the laboratory, and now we are creating a graph which represents what we actually did in the laboratory. So we needed to label our axes so that we can see this very clearly. This graph represents time, and it represents it in seconds. So we label that time, parentheses, seconds, so that we can see clearly what we're looking at. On this axis, these are positions. We have a symbol for position, X with an arrow over top. This means position. If I were using paper and pencil, I might actually write out position here. I don't know that I can. Well, actually, that's not too bad. Position in meters. Position, meters. I've gone a little bit off the scale here. You got to leave enough room so you can make the label. Now when I look at this graph, it can have meaning. I say, how does my position vary in time? Well, it has a quadratic relationship. It varies directly with the square of time. The axis labels give meaning to the graph. Without them, we just have points on a page. They have no meaning. They have no value. So feel free to watch this as many times as you need. There will be other videos to follow which will show you what do we do with this from here on.